In this video, we're going to talk about limits at infinity, is what we call them. So what that means is, instead of seeing what happens as x approaches a specific number, what happens to the y values, we're going to think about what happens to the y values as x approaches a number that's really big or really small. Okay, so x is going to either plus infinity or minus infinity. Okay, so if the y values happen to approach a certain number, k, so a number that exists, as x goes to plus or minus infinity, then we would write the limit, so using the similar notation as before, so the limit as you go to positive infinity of f of x is equal to k, or the limit as x goes to negative infinity of f of x is equal to k. Or if they both go to k, sometimes we also write with a plus or minus. Okay, so to indicate that it doesn't matter which infinity it goes to, the y values approach k. So in any case, what this means for the graph of f of x is that it has a horizontal asymptote. At y equals k, okay, at least on one side, depending on which case you fall into above. So let's look at an example. So suppose we wanted to determine the limit as, first of all, as x goes to infinity of, say, 10 over x cubed. Okay, now because we don't have any really techniques, I'm going to rely on our sort of old one that we shouldn't use, but just to see what happens here, the table of values. Okay, so my function here is 10 over x cubed. Okay, so if 10, we want to take sort of big values of x. Now I'm going to start with 10, which isn't that big. Okay, but let's say I take 10, then f of 10 is going to be 10 over 10 cubed, which is 0.01. Okay, so it's 1 over 100, okay, or 0.01. If I take it bigger, so let's say 10 over 100, or sorry, x equals 100, now I'm going to have 10 over 100 cubed. And here I think that I get 0.4 decimal places and then a 1. So it doesn't take long. We don't even have to go very large to see that these numbers are going to be getting very small. So we might guess that the limit as x goes to positive infinity of 10 over x cubed might go to 0. It seems like that these values maybe approach 0. Okay, what if we do it from the negative side? So same idea. I'm even going to use the same values, but let's negative. Okay, so if I do 10 over negative 10 cubed, negative 10 cubed is negative 1,000. So 10 over that, I'm going to get negative 0.01. Okay, so the same number, but this time it's negative. If I do negative 100, because I'm cubing this negative number, it stays negative. Okay, so this one is going to be negative, and then again 0.4 zeros, and then a 1. So here it seems like that we're approaching 0 again. Okay, but here we're approaching from the negative side. Okay, the numbers are negative instead of positive, but they're still getting closer and closer to 0. So again, we might guess that the limit as x goes to negative infinity of 10 over x cubed is also 0. Okay, so it turns out that is true. Okay, this always happens. So if I have a number, so a real number c, and I have a positive power of x in the denominator, okay, so it doesn't matter if it's a fraction or not, it just has to be positive, then the limit as x goes to infinity of c over xn, and the limit as x goes to negative infinity over c of c over xn, both of these go to 0. Okay, so these limits are approaching 0. So the idea here is that no matter what c is, so c could be 1,000,000. Okay, c could be a really big constant, doesn't matter. The x values are getting, the x to the n is getting so big that it doesn't matter how big c is. Okay, when you take a number and you divide it by a really, really, really big number, you get a number that's really close to 0. Okay, so both of those limits are 0. Now, because these limits exist, we can actually use all of our limit rules with these limits in mind. Okay, so those limit rules that we talked about before, they still apply even though we're going to infinity, x is going to infinity instead of a, because these individual limits exist. Okay, so as long as the limits themselves exist, it doesn't matter really what x is approaching. So let's try an example. So let's say we want the limit as x goes to infinity of 2x squared plus x plus 5 all over 3x squared minus 4. Now, if you are very comfortable with your pre-calculus skills, you might know immediately that this limit is 2/3. Okay, now the reason why is because I have a rational function, so a polynomial over a polynomial. So you can actually just look at the biggest powers. Okay, these powers are going to dominate the top and the bottom. Because they're both x squared, they sort of will cancel out in some ways. So what we talked about before when we were talking about horizontal asymptotes is that when x is very large, this term is so in magnitude is so much bigger than these terms that they actually don't matter. Okay, same with the minus 4. So you could think about it just like this, and then the x squares will cancel and you just get the coefficients. Okay, but we're going to here show how we can actually show that. So if we wanted to show our work, okay, what would we actually do? So let's compute this limit. So what I want to do is use my limit rules together with these new rules that we have above. So I want to write I want to write these in terms of a constant over a power of x. So the trick I'm going to use here is that I'm going to sort of divide every term by the biggest power. And normally they say the biggest power in the denominator. Okay, so that means I want to divide everything by x squared. So I'm going to multiply the top by 1 over x squared, which means I have to also do it to the bottom. Okay, so I multiply by this fancy 1. It has to go into all the terms here. Okay, so now if I rewrite this, so it's going to be 2x squared over x squared plus x over x squared plus 5 over x squared all over 3x squared over x squared minus 4 over x squared. Okay, so we made it look a lot worse, but we're going to simplify each term, and then you'll see why I wanted to do this, hopefully. So the 2x squared over the x squared, though the x squareds cancel, same as they do for the 3 below. And then when I have x over x squared, I can cancel one of the x's there as well. So I end up getting 2 plus 1 over x plus 5 over x squared all over 3 minus 4 over x squared. And now my limit rules say as long as the bottom limit doesn't go to 0, that I can put the limit to the top and the bottom, and I can actually put it through to all the terms. So I'm going to have the limit as x goes to infinity of 2 plus the limit as x goes to infinity of 1 over x plus the limit as x goes to infinity of 5 over x squared, okay, all over the limit as x goes to infinity of 3 minus the limit as x goes to infinity of 4 over x squared. Okay, now we can think about each of these limits separately. So when you take the limit of a constant, so like the limit as x goes to infinity of the number 2, okay, so this limit and this limit of the 3, it doesn't matter what x is because there's no x, okay? The y values are always 2 or always 3, so that's what they're approaching, okay? So these ones are just those numbers. So what about the limit as x goes to infinity of 1 over x? Okay, so that's a constant over some power of x. So that limit is actually going to 0. Okay, so it's going to be a plus 0. Similarly, the limit as you have 5 over x squared, as x gets really big, again satisfies the constant over a positive power of x. So it's also 0. Okay, same on the bottom. 4 over x squared is going to become, as x gets really big, is going to also become 0. So you see that I get that my limit is equal to 2/3, which is what you thought. If you are up to date with your pre-calculus, you might have known that. But because of there's a horizontal asymptote here for this function, at y equals 2/3, because this limit exists and equals 2/3. Okay, so the technique we just used, if you have a rational function, so where f of x is p of x over q of x, where these are both polynomials, and q of x is not 0, obviously, then if you want the limit as x goes to infinity of f of x, or the limit as x goes to negative infinity of f of x, what you can do is divide every term in both the top and the bottom, so in p of x and in q of x, by the highest power of x in the denominator, so in q of x. Okay, and then you just use limit rules, so the limit laws, including the one that we just talked about, so including the fact that the limit as x goes to plus or minus infinity of f of x, those ones all go, not f of x, constant over some power of x, some positive power, so including that those go to 0, to determine the value of the limit. Okay, so that's the idea. Now, I said divide every term by p of x, divide every term by the highest power of x. I multiplied by 1 over the highest power. That's doing the same thing. You could also factor out the highest power of x as well from the top or the bottom. That also works. So this is just sort of an easy way to say it, but there's lots of different ways to think about it. So we'll just do a couple more examples. So here we want the limit as we go to negative infinity, and we have 5x to the 4 minus 15 over x cubed plus 4. So we could divide everything by x to the 3, so the highest power in the denominator, which is x to the 3. Okay, so this is going to be the limit as x goes to negative infinity. So when I factor this through, it's going to be 5x minus 15 over x cubed, all over 1 plus 4 over x cubed. Okay, so when I use the limit laws, so I can put the limit through as long as the bottom limit doesn't go to 0. Okay, and now these 2 at the end here, because I have a constant over a power of x, okay, that one's 0 and this one is also 0, so those approach 0. The limit on the bottom, because it's already 1, it just is 1, so it approaches 1. So I end up with the limit as x goes to negative infinity of 5x over 1. Okay, which is, so maybe actually I'll include the zeros. So this is minus 0 and also plus 0. So basically it's just the limit as x goes to negative infinity of 5x. So now this limit isn't going to exist, so it's not going to a nice number, but we can tell that it's going to negative infinity. Okay, so this is still a DNE case, but it's going to go to negative infinity because it's 5 times a really, really big negative number, so that's still going to be it's going to be an even bigger negative number. Okay, so our limit here doesn't exist, but it approaches negative infinity. Now, one thing I should comment on is that we don't have the plus or minus here, but these limits at infinity are all one-sided limits. Because obviously, if I'm approaching, if x is going to negative infinity, I can't really approach negative infinity from the left. How do I get smaller than negative infinity? Okay, that's as small as it can be. So these limits at infinity are all, in fact, one-sided limits. So you can only approach from the side that makes sense. Okay, let's do one more. So this one does not look like a rational function. Okay, so there's different ways you can approach this. So we want the limit as x goes to infinity of square root x squared plus 3x minus x to the 5/2. So the first thing, what would happen if we think about putting in a big number? Okay, so I'm going to have a big number squared, that's an even bigger number, plus 3 times a big number, so I'm making it even bigger. Now I take the square root, it's still a really big number, okay? It's not quite as big as it was, but it's still really big. So this first term is it's going to infinity, positive infinity. Now, what happens when I take infinity to the power 5/2? So remember, 5/2 is a 5th power and then a square root, or a square root and then a 5th power. Okay, either way, it's also going to infinity. Now, what happens when we have infinity minus infinity? Okay, this is actually an unknown form. We call it an indeterminate form. So anything could happen. Determinate form. Okay, so we need to do some work to see what happens here. Now you might be able to reason out that the second infinity is going to be a bigger power, so it's going to win in some sense, but we're going to see how that happens. Okay, so the first thing I'm going to do is I kind of want to factor out as many x's as I can. So it's hard to do this with a square root, but what I'm going to do is try and pull out the biggest power of x in the square root. So that's x squared, and then I'm going to have 1 plus, now it's going to be 3 divided by x left over. Okay, now the reason I want to do that is because now I can break it apart. Okay, so it's the square root of x squared times the square root of 1 plus 3 over x. Okay, now when I square a number and then take the square root, what do I get? Well, this is the special case where I actually get absolute value x, because I'm always going to get a positive number. But our x's are positive anyway, because we're really, really big. We're going to positive infinity. So you don't really have to worry about that absolute value. So maybe I'll keep it in this step and then I'll drop it. Okay, minus x to the 5/2. So that's right on the side here. Absolute value x is actually equal to x. Since x is going to infinity, therefore it's positive. Okay, it's a positive number. So now what I'm going to do is pull out the biggest power of x, okay, which here is x to the 5/2. Okay, so up here, the absolute value of x is like x to the 1. So I'm actually taking out 5/2, which means that I have -3/2 left over. Times the square root, 1 over 3, 1 plus 3 over x. And now it's going to be -1. Okay, on that side. Okay, now again, I could rewrite this. Okay, so when I have a negative exponent, it's like being on the denominator. So I have 1 plus 3 over x inside my square root, all over x to the 3/2. Okay, now if I think about computing this, okay, x to the 5/2, this is still going to infinity. Okay, so that's going to positive infinity. What's going on inside this bracket? So the 3/x, so remember the limit can go inside, so I can do the limits separately as long as I don't get anything crazy. So I want to know if this limit in the brackets here turns out to be a nice number. Okay, so the limit of 3/x, okay, that's going to 0. So that means that this numerator is going to square root of 1, which is just 1. Okay, and now when I take a constant divided by a positive power of x, that actually goes to 0. So this thing in the brackets is going to -1. So if I take positive infinity and I multiply it by -1, I'm going to get a really big negative infinity. Okay, so again, I got a limit here that didn't exist, but I know that these are going to be really big negative numbers. And it kind of makes sense if we go, it should make sense if we go back up to the original question. Okay, this part, the first infinity that we got, has sort of the highest power of x is like x to the 1. Okay, whereas the second part is x to the 5/2, so it's 2.5. So in magnitude, it's bigger. So that means this sort of minus infinity is going to be much bigger than this first infinity, which is why we end up with a minus infinity at the end. Okay, so those are just a few examples of how to work with limits as x goes to plus or minus infinity.